In continuing with topic 3, paper 12, we're going to revisit the calculation of standard deviation for a two-asset portfolio because we are now going to use that formula in an example. So just to remind you, at the bottom of page 3.10, there is the formula for standard deviation of a two-asset portfolio. Remember, we take the weighting of the first asset squared multiplied by the standard deviation of the first asset squared plus the weighting of the second asset squared multiplied by the standard deviation of the second asset squared plus 2 multiplied by the two weightings multiplied by the correlation coefficient between the two investments, then multiplied by standard deviation of the first asset and standard deviation of the second. Do I need to know this for the exam? Unfortunately, yes. So as I said before, memorize it, go into the exam, and when the exam starts, not before, write it down on a piece of paper so you can refer to it. Okay, so what's the example with that formula in mind? Top of page 3.11. You're given a two-asset portfolio with 70% invested in asset A, expected return of 12%, standard deviation 1.3%, and 30% is invested in asset B with an expected return of 20%, standard deviation of 1.6. And we're told the correlation coefficient between these two assets is negative 0.9%, almost perfect negative correlation. So this is a good combination to reduce portfolio risk. We're asked to calculate the expected return and the standard deviation of the portfolio. Now, the expected return is straightforward. It's a weighted average. So we take the weight of the first investment, that is investment A, we take 0.7 because it's 70%, well, we take the decimal, 0.7 multiplied by 12% plus 0.3, the weighting of the second investment multiplied by the expected return, 20%, add those up, 14.4%. That's the expected return of this two-asset portfolio. Now, what about the standard deviation? Well, there's the formula that I reminded you of. Instead of the square root, we're raising it to the power of half, which is the same thing. Okay, we plug in the numbers. Now we're saying the variance, that is the standard deviation squared, is equal to, and then we'll move on to take the square root. There's the weighting of the first 0.7 squared multiplied by the standard deviation of investment A, 1.3 squared. Then we add to that the weighting of the second investment, 0.3, the 30% squared multiplied by standard deviation of the second investment, 1.6 squared. Plus 2 multiplied by the product of the weightings, so 2 multiplied by 0.7 multiplied by 0.3, and there it is, the correlation coefficient multiplied by minus 0.9, and then multiplied by the two standard deviations, 1.3 and 1.6. We run the numbers. Now you'll see that the effect of the negative correlation coefficient means that the third factor in this equation is negative, and that is significant. We do the calculation, we get the variance of 0.27226. If we take the square root, we get the standard deviation of this two-asset portfolio as being 0.52179. And that measure is in percentage. So we're saying that the expected return, 14.4%, with a standard deviation of just over 0.5%. So it's fairly small. Now, continuing with the formula, if I plugged in a correlation coefficient of -1, and that's perfect negative correlation, which is unusual, but very attractive, we run through the numbers and we get 0.43. So that standard deviation is even lower than the one where the correlation coefficient was -0.9. If we put in a correlation coefficient of 0, so there is no correlation whatsoever, we get a standard deviation of the two-asset portfolio of 1.0288%. So that is higher than the previous two. And then if we look at a correlation coefficient of +1, we put +1 into the formula, run the numbers again, we get a correlation coefficient of 1, I beg your pardon, we get a standard deviation of the two-asset portfolio of 1.39. Now that is the highest standard deviation. And we cannot go any higher because just below it, you will see that a weighted average of the two standard deviations is 1.39. In other words, if we've got a correlation coefficient of +1, there is no benefit of bringing those two assets together in terms of reducing the standard deviation of the portfolio. Another way to look at this is as long as the correlation coefficient between two assets is less than +1, then there is benefit of bringing those assets together to lower the portfolio risk, the portfolio standard deviation. And that is why diversification in portfolio asset management is attractive. So top of page 3.12, we're told the above example shows portfolios the same expected return of 14.4%, because that does not change, have different levels of risk depending on the correlation between the individual assets. We have the least risk when you have perfect negative correlation. That means correlation coefficient -1. Moderate risk when correlation coefficient is 0. And most risk, in fact, the weighted average of the individual risks, where there's perfect positive correlation, where the correlation coefficient is +1. That takes us on to the efficient frontier. Now, what Markowitz did after calculating different expected return portfolio standard deviation combinations for different correlation coefficients, he plotted all those portfolios on a graph in terms of return and risk. And by changing combinations, by changing correlation coefficients, he endeavored to move to the left and to the top. That is, can I reduce the risk further for a given return? Can I increase return for a given level of risk? But there was a point at which he could move no further, and that is represented by this hard line. We call it the efficient frontier. A, B, C represents lowest level of risk for each possible level of return. B and C are not efficient because any investor can get a better return for the same level of risk. That is why we look at A, B being the efficient frontier. And for some reason, we've given you the formula for the standard deviation of a two-asset portfolio once again at the bottom of page 3.12. Okay, let's now move on to looking at investor preferences, because what we're going to do is we're going to combine the concept of the efficient frontier and investor preferences through indifference curves to explain why there is the most preferred combination of investments for individual investors. So at the top of page 3.13, which portfolio on the efficient frontier would an investor prefer? We're sort of looking for a process, a framework to explain why different investors prefer different portfolios. To be able to answer the question, we have to understand investors' individual preferences, I should say, and we explore indifference curves to do so. What are these indifference curves? Set of utility curves showing different levels of satisfaction or utility for each investor. What we're saying is when we're looking at one of these curves, an investor is indifferent to choosing one portfolio rather than the other. So we can move up and down these indifference curves in terms of portfolios of expected return and risk. An investor has no particular preference. They're quite happy to be anywhere on that indifference curve. Now, an investor will strive to be on the highest indifference curve because for a given level of risk, they will want the highest return. And we're told at the bottom of page 3.13, the slope of the indifference curve reflects the degree to which an individual is risk averse. So flatter the curve, more risk tolerant an investor is, happy to take risk. Steeper the curve, more risk averse the individual is, and an aggressive investor, more risk tolerant than the conservative, therefore aggressive investor will have flatter curve. So we combine on page 3.14, we combine investor preferences with the efficient frontier. And the idea is for an individual investor, if they were able to draw their indifference curves and they had an efficient frontier in front of them, they will be looking to move to the portfolio on the efficient frontier that is at a tangent to its highest indifference curve. And the example we're looking at for this particular investor, it would be portfolio A. Now, in reality, do we draw these curves and put in the efficient frontier? Highly unlikely. No, an investor, consultant, wealth manager will ask questions of a client and then will come up with a combination of investments that reflects the expected return risk combination that they believe is optimal for that investor. Now we're moving on to the capital in asset pricing model. Now this was developed by William Sharp and gives you a calculation of the required return for a particular investment for an investor. The overview up top says the capital asset pricing model seeks to measure a security or portfolio's return relative to a benchmark being the market portfolio. Right, we're going to get into this in a lot more detail. Expected return on an equity given risk-free return and the risk-weighted market premium. So the formula, expected return for a particular investment is the risk-free rate. An investor wants the risk-free rate as an absolute minimum. And then they want a risk premium that reflects the risk inherent in the investment we're looking at, investment I. And we multiply the beta of this investment, and we'll come to beta in a moment, multiplied by the market premium. That is the return of the market minus the risk-free rate. In other words, the market is providing a premium over the risk-free rate. That's what we would expect, but we're looking at the market as a whole. So let's say the market is generating 5% above the risk-free rate. How much of that 5% do we want to add on to the risk-free rate to get our required return? Well, it's going to be in relation to the volatility of that investment relative to the market as a whole. So if the investment we're looking at is twice as volatile as the market, beta will be 2. You'll want twice the market premium. But if the volatility of the investment you're looking at is half of the market, beta would be 0.5. So we apply beta to the market premium to get the risk premium that we wish for investment I, and we add it to the risk-free rate, and that's our expected return. Let's look at an example, capital asset pricing model example. What is the expected return on shares of GrowCo Limited if the expected market return is 5%, the risk-free rate of return is 1%, and the company beta of GrowCo is 1.5. It's 1.5 times as volatile as the market itself. And we'll see later how we calculate beta. Well, the expected return, given the beta of the stock, is the risk-free rate, 1%, plus 1.5 multiplied by the market premium, which is 5% minus 1%. We're expecting a return for this investment of 7%. Now, how we actually use this measure, we will deal with in the next lecture.